Video we will learn how to design the elevated reinforced concrete water tank in Etabs. So the given scenario is shown. The height of the water tank is 20 feet for pressure requirements. The diameter of water tank is 20 feet maximum allowed. The material properties to be used are shown. The capacity is to be 22,000 gallons. The soil type is SD, seismic zone 3. Wind speed is 100 miles per hour. Wind exposure type C. We have to use 4 columns. The 2 of them are shown on the figure. We have to design the tank columns and the bracing at the mid height. We have to detail the structure using Autocad in the end. So first we will calculate the column base offset. For this we need 3 important things: the approximate tank load, seismic base shear, and the base shear due to wind load. First we will calculate the approximate tank load. Since the water is to have a volume of 2941 cubic feet, so the approximate weight will be 184 kgs, and the concrete weight roughly varies between 50% to 2 times of the water weight. So conservatively we will take twice of the water weight as concrete, which gives us 370 kgs approximately. So the total weight, adding water weight and concrete weight as dead load to attract seismic base shear conservatively, is 554. Using UBC 97 to calculate the base shear, we need parameters like coefficient of acceleration, coefficient of velocity, importance factor, and the strength reduction or ductility factor using ASC 710 chapter 15 for elevated water tank. The formulas to calculate base shear and their upper and lower boundaries are used from UBC 97. The parameters which were extracted from UBC 97 are again shown. The value of R and the time period is first calculated. 10 feet as approximate tank height gives us 0.256 seconds. The base shear comes out to be 584 kps. Calculating the upper and lower limits. The upper limit is 249 kps and the minimum has to be 32.9 kps. So the maximum upper limit governs as 249.3 kps. Now going to wind shear calculations using UBC 97 table. Importance factor is the wind stagnation pressure using UBC 97 equations. Tank height is approximately volume divided by the base area, that is 10 square. Actually it's mistakenly written 102. Take tank height as 10 feet around to account for freeboard as well. The pressure comes out to be 28.3 psf, which gives a roughly shear value of 5.65 kicks. Now we have seismic base shear and wind shear. We can compute the column offset. So the higher value of base shear is 249 kps due to earthquake, which will be used for the calculation of base offset of the column. For that we will use the basic equilibrium equations of moment. The reaction on each column is 138.5 kps gravity reaction due to weight of the water tank and the water. Tank height is approximately 10 feet. Ignoring the moment due to weight of the water in case of tank is empty, and conservative weight to balance the base shear. So we take the moment about the red circle. the minimum lever arm which we need from the center of the column as x by 2. The value of x comes out to be 22.5 feet. So the tank dimension finalization gives us 20 feet allowed diameter and the height as 10 feet. The maximum allowed height is roughly, practically talking, diameter divided by 1.5 times, which we provided 10 feet. So we are within the limits. Starting with the Etabs part, first we will define here rough numbers which we will edit then in the grids. Now we will be editing the grids. Since the tank is cylindrical, we have to design a cylindrical system. If you don't understand the circular grid definitions, you have to see the video for defining circular grid system in Etabs, which I have explained in detail how to define the circular grid system in Etabs, whose link is also given in description. Since the column offset is to be of 1.25 feet from the tank outer dimension, as the tank diameter was 20 feet and the column's base diameter or the offset distance is 22.5 feet. So we specified accordingly. I will start with the material properties. 5000 psi for concrete and 60,000 psi or 60 ksi for rebar. We will be deleting the extra sections given in Etabs by default. In next videos we will be focusing on steel structure. This may be approximately conclusion with the concrete structure videos. So defining the columns roughly as 18 inches in diameter, then we'll define a 21-inch column and then a 24-inch column with increments of 3 inch in diameter. So if 18 inches column does not pass the stress check, we will have to increase the column diameter to 21 inches, which we would have already defined here. Now defining the retaining wall or shear wall. Basically it's a retaining wall for the tank, but in the end we will be using the shear wall Excel sheet which we used previously in design of shear walls, as the percentage and distribution of steel is somewhat similar. Approximately defining a section of 8 inches thickness and 10 inches thickness. Then we'll add a property. Actually I'm wanting to add an auto select list. Here we go, we can add an auto select list. Let's name this as auto select list or auto select. Taking slab thickness as 10 inches initially, as if the slab does not pass or fail or is over designed, you will have to check according to the video whose link is given in description for slab design. So that is the location where column will come in 3D, the retaining wall of tank. Now I'll be modeling the bottom slab of the tank. Now I'll replicate this slab to the top as well once I'm done with making the columns and all the other things. Actually I'm noticing the column wouldn't come in this grid system at an equal distance. As you can see, 4 columns cannot be placed at equal distance in this grid system. Let's modify the grid system in which we get 4 equally spaced columns. We have to do number of trials, or you may divide equally the grids as such so that the 4 columns can come at equal radial spacing. Let's make the spacing as 36 degrees so that we get 10 lines to make a complete 360. Still I won't be getting 4 columns at equal spacing. So you might encounter these kind of problems when you have to space the columns. The fine the meshing or the grid, the slower will be the model. Let's divide the 360 degrees with 12, which is multiple of 4, making all spacings as 30 degrees. Now we can definitely place 4 columns. To make a complete circle, I have added further spacings. Okay. You may hide these annoying bubbles. Once we are done hiding, now we can model the slab on it. Now we need to replicate the slab to a story above. Now the thing left in modeling is the wall. Now let's save the model. Adding the load patterns. Notice that I will be adding the dead load, the water load as dead load because it will be in base shear. As base shear is due to the dead load only, so conservatively adding the water load in dead load so that it helps in getting the base shear values. Assigning the water load of 10 feet height to the slab. As in first part we will be designing the columns. Assigning the diaphragm for distribution of lateral loads such as wind and earthquake. Defining the parameters for seismic load and wind load. Now the wind load and seismic load is defined. We'll be defining the P delta. Reference for this 1.2 value is CSI website. If there would have been a live load, we would have taken a multiple of 0.5 for that. The loading code and the design code have been set. Now we'll be adding the default combination as per ACI code. Making the bottom as fixed as the structure would have its foundation, which can take up moment as well. That means no pile foundation. Designing the concrete frame. So you can see the columns have failed the stress check. The reinforcement exceeds the maximum allowed. That means the column are failing. So we need to assign a larger cross section, assigning a 21-inch cross section diameter, and then designing the frame. So the columns have passed. Let's check the percentage of steel, whether it's placeable practically on site or not. Preferably a size or a percentage of 4 is desirable as maximum. However, code allows a value of 8% as maximum. But let's increase the cross section, as increasing concrete cross section and keeping reinforcement lesser than 4% is economical and practically more easy to execute. So checking the percentage at 24-inch diameter column, which is around 2 and 3. So that is okay. Now we will be detailing the columns first in the Autocad. Longitudinal reinforcement to be shown in inch square. We'll divide the reinforcement in number 9 bars, which has an area of 1 inch square roughly. Number of 9 bars gives us 12 number 9 bars. Now checking the shear steel or the ties, which we set to ties instead of spiral. You may use the spiral option as well, which we defined in the frame sections. Select the highest value as the columns have to be set the ties. Now the shear spacing ties is 12 times area of the bar into divided by area of shear steel, which gives a spacing of 22 inches, which is practically too high. So we'll apply the limitations of special moment resisting frame as it is in high seismic zone. So I am quoting the ACI 318 clauses. The similar clauses are given in ACI 2014. So we'll calculate these spacing limitations for our case. 6 times diameter of the smallest longitudinal bar, that is number 9. So gives us 6.7. The next check gives us 6 inch and the last check is 6. So we will provide number 3 bars ties at 6 inch center to center. So the cross section of column is given as section 1 which we will be detailing here. Let's detail it as 12 number 9 bars. Number 3 or 3 wide diameter bar at 6 inch center to center. We need to make 12 of these dot bars, which are the longitudinal reinforcements. I'm placing the bar roughly, however they need to be equi-spaced. Just to demonstrate. After the column design, we have to design the circular slab whose wing is given in description. Now for the tank wall design, we need to remove the load from the base of the slab and then assign the VDL load to the water tank. Otherwise the base shear would have been increased a lot. So there are 3 local axes. The local axis for our concern to assign the tank water load is local axis 3, which is shown in blue. Actually there is a mistake. The blue color is local 3 axis as shown in the video. So we need to assign in local 3 axis here, for which we need to calculate the C and D factors, which comes out to be 0.624 and the other as minus 0.624. Now since we will be designing the walls, so we will apply the VDL to the walls. Selecting the walls in order to assign the VDL to the wall. Now assigning the non-uniform load as calculated C and D parameters and to be assigned in local 3 axis, that was blue direction. Adding the number of pairs so that we may assign each wall segment a single pair name. There are 12 segments to 12 pairs, one for each wall. The design code for the walls is ACI31814. Adding default combinations for the wall design. Checking whether the combinations are imported by the preferences. So okay, we will be running the analysis and then the design of wall, which is shown as here. You may check the design summary here by right clicking on a single wall segment. It shows various parameters such as design combination used and the values of shear and moment. For us, the important thing here is to use in Excel sheet is the length of the segment, which I will start inputting in the Excel sheet. You may download the Excel sheet from the link given in description. A thickness to be selected by Etabs, which we have to check what thickness it has selected from the auto select list, which is 8 inches. So we'll be unlocking the model and manually assigning it as 8 inches to keep the uniform. Now since the required reinforcement ratio is in millimeter units, so we need to convert or change the units in millimeter. Select the highest number you can see from there to put it in here, as the tank is symmetric and the loading should have been equal. Let's go for number 3 or number 12, number 4 bar. Diatrend refers in MK system as number 3 bar. Practically don't set a spacing greater than 10 inches. Now for the horizontal or shear steel, you need to go back to Etabs and select Beer Shear Reinforcing, which is in mm per meter units. So the wall design is shown on the right of the sheet. Now we'll be detailing the sheet or the wall in Autocad. Number 3 at 10 inches, as 250 mm means 10 inches. Now as far as foundation of the structure is concerned, I may show you how to extract the loading values, and then for foundation design You may also check the video whose link is given in description, that how to use these values for foundation design within Etabs and an Excel sheet, which I have already prepared for you. You may get it from that video. So that was the complete elevated water tank design. Thank you for watching.